So my name is Azul Portillo, and today I will be presenting Lab 9, where my group and I investigated how the magnetic field inside a coil changes when we increase the number of loops or turns of wire. My group and I's goal was to understand this relationship using Ampere's law that we've learned about in lecture and in lab, and from direct measurements from our equipment. Our introduction. In this lab, we focused on the idea that an electric current always creates a magnetic field. Ampere's law tells us that the magnetic field inside a coil is directly proportional to the current and to the number of loops in the coil. So if you keep the current source the same, but increase the number of loops, the magnetic field should increase as well, because more loops also means more wire length. And also the resistance of the coil increases as well. But the main idea that my group and I wanted to test was whether doubling the number of loops will also double the magnetic field. And that was our hypothesis that we wanted to prove in this lab. So, materials. For this experiment, we used the Capstone software, the coils, one of 200 loops, and then the other one's 400 loops, the Pasco current generator, the current sensor, the computer, a calculator, a stand with a clamp, and then the leads that were necessary to connect the circuit. In this slide, you can see the coils that we used, one with 200 loops and one with 400 loops. The blue coil is the one with 200 loops, and the other coil was the one that was 400, obviously. And these two coils allowed us to directly compare how magnetic field strength changes when the number of turns is doubled. Moving on to experiment setup. So to begin, my team and I connected the Pasco current sensor to Capstone and selected the digits display to read our magnetic field measurements. We set the measurements to milliteslas, since magnetic field values inside these coils fall in that range. Then we mounted the coil we wanted to test on a stand with a clamp and connected the leads from the current generator to the coil. This did allow the current to flow through the wire and create the magnetic field that we wanted to measure and compare. Continuing with our equipment setup, next we place the magnetic field sensor through the center of the coil. The magnetic field inside the center we know is the strongest and the most uniform, so this would give us the most accurate reading for our experiment. We started recording first, then quickly inserted the sensor into the coil and wrote down the maximum number that we got, the maximum reading, which typically appears immediately, and it did appear immediately for us when we did it. This procedure helped us limit any error from movement or angle or weird positioning changes. Moving on to experiment development part 1. We first measured the magnetic field using the 200 loop coil. After running the current and positioning the sensor, our measurement turned out to be 26 milliteslas. So this was our baseline value. And you can see right there on the computer the recorded measurement and then our setup for this first part of the experiment. Moving on to experiment development part 2. We repeated the exact same procedure, only this time we used the 400 loop coil. Again, we inserted the sensor into the center and recorded the peak value. This time we did observe that the measurement was 50 milliteslas, not 500, 50 milliteslas. So even before calculations, we were able to see that the magnetic field almost doubled, which was really cool to see and nice to see because it meant we were doing things right. So now moving on to experiment development part 3. So to check how close we were to doubling, we calculated the percent difference using the formula that RTA gave us, or this formula right here, V1 minus V2 all over V1, where V1 is the 200 loop coil measurement, which was 26 milliteslas, and then V2 was the 400 loop coil measurement, which was 50 milliteslas. Inputting those numbers into the formula was 26 minus 50 divided by 26, which gave us a 92% increase. This was very close to the ideal 100% increase that we did expect if doubling turns truly double the magnetic field strength. My group and I kind of concluded that the minor differences were likely due to measurement error or alignment of the sensor that could have been weird, or slight variations in the current. Okay, moving on to data analysis. So from our measurements, we confirmed that the magnetic field strength increases when the number of loops increases, and that the relationship is almost directly proportional, just like Ampere's law predicts and has taught us. When we doubled the coil from 200 loops to 400 loops, the magnetic field increased from 26 milliteslas to 50 milliteslas, which is very close to doubling. This showed us that the number of loops, magnetic field strength, and current are proportional to one another. And lastly, for our conclusion, in conclusion, our experiment successfully proved our hypothesis that we came up with at the beginning. We were able to set up and run the experiment independently by applying our understanding of Ampere's law. This was kind of the hardest one because RTA said that he was not going to help us and that we kind of had to do this on our own and with our own creative brains. So it was nice to see that our results showed a nearly proportional increase in magnetic field strength when we doubled the number of turns in the wire. So once again, this confirmed the theoretical prediction that we came up with. And that is the end of Lab 9 and our last lab. Oh, and then we have the credits. So here are our group numbers listed below. Everyone contributed to completing the lab, collecting data, and putting together this PowerPoint. So we have Azul participated in lab, experiment setup, and then that's me. So I did the voiceover in the video. Carola did participate in the lab. Diana participated in the lab and wrote experiment development. Jacob participated in the lab, wrote the data analysis and also the conclusion. And Monse participated in the lab. And that concludes this voiceover. Thank you and goodbye.